Hello everyone, and welcome to the Kinetic Energy Post Lab, during which we will create graphical and mathematical representations of the relationship between the kinetic energy, the speed, and the mass of an object. In other words, our goal here is to create a math model for kinetic energy so that we can calculate an amount of ability to produce change due to the motion of an object. And objects that moving are producing change because they're changing position. Well, you first created a graph of kinetic energy in joules, our energy unit of joules, versus speed in meters per second. When you graph that, you did not get a linear graph. You got a top-opening parabola. Well, we've seen top-opening parabolas before, right? And so hopefully you saw this and you said, to linearize it, what must I do to the speed? I must square it. So you graphed kinetic energy in joules versus speed squared in meters squared per second squared. Notice you have to square the units as well. And that, in fact, gave you a linear graph. But not just any linear graph, one that goes through 0, 0. Now, why is that important? Because we have learned this year and last that if you... Why is that important? Because we have learned this year that if you graph two variables and it ends up with a linear graph that goes through 0, 0, that tells you that those two variables are proportional to one another. But now be careful. It's not kinetic energy proportional to speed. Look, right? That's not straight, linear, it goes through 0, 0. It's kinetic energy proportional to speed squared. All right, which means that changes in speed get squared, and that's going to have a big effect on the kinetic energy. Say, for example, you're driving through your subdivision at roughly 25 miles an hour, okay? And you want to stop. Well, you have to dissipate a certain amount of kinetic energy to stop. But now, let's say you take that same car and you're driving on M59, where maybe you're going twice as fast as you would in a sub. Now, how much energy, kinetic energy, do you have that you need to dissipate to come to a stop? It's not 2 times the kinetic energy. It's speed squared. So if you're going twice as fast, you have to dissipate 4 times the kinetic energy. Right? 2 squared is 4. 4 times the kinetic energy. And if you're out on US 23, where you might be going 3 times as fast as in a subdivision, right? Now you don't have 3 times the kinetic energy to dissipate. You have 3 squared, or 9 times the kinetic energy to dissipate. It's going to take you much longer, right? Much longer distance-wise to brake to a stop on the highway than it is in your sub. In fact, in the highway, it might take 9 times as far, right, as it would in a subdivision. And so it's important that you leave even more space between you and the cars around you, right, if you're going at faster speeds. So this little speed squared shows you that the speed really affects how much kinetic energy you have. Now, since we linearized this second graph, we can make a math model out of it. Of course, our old friend y equals mx plus b. The y variable is what we graph on the vertical axis, the kinetic energy. And that's going to equal your slope. Now, you're all going to have slightly different slopes depending on setup, and we'll talk about why they're different. But according to when I did this lab, I thought the theoretical slope should be around 0.14. All of your slopes were pretty close to 0.14, give or take a tenth or so, right? We'll discuss what that means in a little bit, okay, or where it came from at least. Now let's check out the units of that slope. These are fairly complex, right? Slopes are rise over run, so that's where the units come from. So the units of rise are joules. The units of run are meters squared per second squared, because we're doing the linearized graph, right? Now, this doesn't look like it simplifies at all. But remember that a joule is a derived unit. It's a combination of other base units. And you might remember that we defined a joule as a Newton meter. Like taking something that weighs a Newton and lifting it 1 meter is 1 joule of energy. Well, now things start looking a little more like we can reduce things. But remember that the Newton is itself a derived unit. A Newton comes from F equals ma, the Newton's second law. 1 Newton is the force required to make a 1 kilogram object accelerate at 1 meter per second squared. So, a Newton is a kilogram meter per second squared. But you see what I did here? So a joule is a Newton meter, and a Newton meter is a kilogram meter per second squared times a meter. Now things will cancel. These two meters go together to make a meter squared, which cancel out with the meter squared on bottom. The per second squared on top cancels out with the per second squared on bottom. And look at what we have left. Kilograms. So the reduced units on our slopes are actually kilograms. Well, what do we measure in kilograms? Yeah, mass. So certainly the units seem to indicate that this slope has something to do with mass. Now, you might be able to see it already, but if not, hang on. All right, we'll go a little further with it in a little bit here. The x variable is what we graph on the horizontal axis. Well, that's not speed. That wasn't linear. It's speed squared. Right, speed squared. And the y-intercept? Well, both logically and using the 5% rule, it should work out to be 0, 0. I mean, think of the logic. What does it mean to have 0, 0 on these graphs? Either one, really. 0, 0 means when the speed is 0, so is the kinetic energy. And certainly that makes logical sense. Kinetic energy is the energy of motion. If you're not moving, right, then you're not producing change. So this is our math model here for kinetic energy. But let's talk a little bit here about this slope, all right, and what it means. You might remember that in this lab, while we varied kinetic energy and speed, right, one thing we didn't change was the mass of our cart. We didn't add or take off masses during the lab, right? We just used the same cart the whole time. And your cart has a mass around 0.28 kilograms. Might be 0.29, all right, but right around in there, kind of depends. So around 0.28 kilograms. Now, do you see the relationship? Well, let's look at all the data. Right, if we go to the Google form where we gathered all this stuff up, here are like, I think 35 data points, okay? Don't worry about these two columns. Look at these two columns to start out with. Here's everybody's slope. Notice everybody's slope is pretty close. They're all 0.1 somethings, either 0.13s, 0.14s, here's a 0.15, right? So they're all pretty close. So they average out to about 0.14, 2 sig figs. Here's everybody's cart masses. Again, all pretty close to one another. Around 0.28, maybe a few 0.29s here or there, right? So it averages out to about 0.28 on average. Well, look at those numbers, right? They both have the same units. They're both in kilograms. What's 0.14 compared to 0.28? Looks to be about half, right? Just to convince you here, I created a column. Actually did a little thing here where I took the cart mass and multiplied it by 0.5. I took a half of it, right? So if you look at the cart masses, half the cart mass compared to your cart mass, you can see that, you know, that's what you get here. And then I did a little percent error calculation between your slope and half your cart mass. And you can see the percent errors here. So sure, there were some groups that had some pretty small errors, and there was a couple of groups that for whatever reason had some big errors. We're going to talk about some sources of error. Here's a negative 10%. Here's a couple of positive 8s. Here's a positive 10, right? But in general, the slopes were pretty small. And one of the cool things and why we do this lab multiple times in multiple groups over multiple classes and average them all together, because look what happened. Half our cart mass and our slope, at least to 2 sig figs, ended up being exactly the same thing. So on average, over the course of these periods, we ended up with 0% error, which should be pretty convincing, right, that your slope was supposed to be half your cart mass. You with me? Well, some of you did have some error, right? So let's talk about that. So it looks like the slope is about half the mass of the cart, right? Where are some sources of error here? Well, a couple of places. First off, as we talked about, the masses of your carts weren't all exactly the same, okay? Some were 0.28, some might have been a little closer to 0.29, so that might vary a little bit. I assumed a 0.28, right, in order to have something to write down. The second one, though, is probably a bigger source of error. You remember in the part of the lab where you had both the position time and velocity time graphs on the same set of axes, you had to kind of get to the nearest point to the position you wanted to look at, right? And maybe you couldn't get at exactly 0.1, 0.2, 0.3, 0.4 meters and so on, right? Maybe you were at 0.11 or 0.12 or 0.99 or something like that, right? So that threw those off just slightly. So there might be a little error there. Probably the biggest error, though, was how well the first half of your lab went and how accurate was your effective angle, which, if you remember, was the angle of the track that acts like there's no friction, because there actually was a little friction with the carts, right? So we used the effective angle to try to mask that effect of friction and get that out of there, so we didn't have to worry about the dissipated energy aspects of things, so that at the bottom of the hill, it was all kinetic. And so that was probably a big place where error took place here, was how accurate your effective angle was. But again, that's why we do this multiple times with multiple groups, and that's why it's great to average that all out, because really, on average, your slope was half the mass of your cart. And if we plug that in, we come up with a math model for kinetic energy that might be familiar to some of you, that the amount of kinetic energy stored in a moving object is 1/2 times the mass times the speed squared. 1/2 mv squared, as it's often said. This is a very popular equation across science, right, to look at the energy stored in moving things. Note, speed is squared, though. So changing the speed has a bigger effect than changing the mass does. Sure, if we had piled twice the mass on the cart, right, made the cart twice as massive, we would have gotten 2 times the kinetic energy at the same speed, right? But if we double the speed, we get 4 times the kinetic energy. So that squared is important not to lose. It's a lot like elastic potential energy is 1/2 kx squared. Sure, changing the spring constant affects the elastic potential energy, but changing how much it is stretched or compressed is squared, so that affects it even more. But just to convince you that this isn't a made-up equation, let's check out the units here that we get from it, okay? Mass is, of course, in units of kilograms. Speed would be in units of meters per second, which gets squared, so that's a meter squared per second squared. So this doesn't look like much, right? It certainly doesn't look like anything energy related, but let's see if we do a little algebra on this. So first, I want to factor out a meter, right? We've got a meter squared here. So if I pull that to the outside, everybody okay with that, right? That's a meter, that's a meter, that's a meter squared. So now we're left with kilogram meters per second squared times a meter. Do you see it? What's a kilogram meter per second squared? Yes, that is a newton. And what's a newton times a meter? Our old friend, the joule. Right? So as long as we're using units of kilograms and meters per second in this equation, we are going to get out joules of energy. Right? Another important little dimensional proof that it's got to be mass and speed squared in this equation in order to give us the units of joules. So now we have created another math model for our energy storage mechanisms, right? Which really only leaves us with a few things to do, which we're going to talk about in the next few days, right? So we can complete this energy unit and start using these things. So I hope you enjoyed this kinetic energy post-lab.